As everyone knows, electricity is used throughout the automobile. There are many electrical systems and components, such as the headlights, rear combination lights, windshield wipers, power windows, audio, air conditioner, and so on. How is power supplied to these components? In this video, we will take a look at the relationship between the power supply and electrical loads, the principle of the generation of electricity, the construction and operation of the main components of the charging system, and how to troubleshoot the system. One of the sources of power for the electrical components is the battery. The other is the alternator. The starter motor and the ignition system are electrical components for the gasoline engine. But there are other kinds of electrical components in other parts of the automobile. From the point of view of the power supply, these devices are all electrical loads. We all know that when we connect an electrical load to a power supply, current flows. When the ignition switch is turned to start, current flows from the battery to the starter motor and the engine starts. Then, the alternator starts to generate electricity and current flows to the ignition system. At the same time, the alternator sends current to the battery to charge it because the battery was discharged during starting. In addition, when the headlights, the windshield wipers, and the other electrical components are operated when the car is running, the alternator generates the necessary current for those also. In summary, the alternator, which is the main component of the charging system, not only supplies current to the electrical components of the automobile, but also charges the battery. How does the alternator generate electricity? We will now explain the principles of the generation of electricity. Here is a magnet and a coil of conducting wire. When the magnet is inserted into the coil, the needle of the microammeter connected to the coil moves. When it leaves the coil, the needle moves again. This shows that the coil generates an electric current, and when the magnet is moved faster, the current is stronger. The magnet produces lines of magnetic force running from the North Pole to the South Pole. This forms a magnetic field. Electricity is generated when the coil cuts across the lines of magnetic force. This is called electromagnetic induction. This multi-layered coil generates more current than the previous one. In addition to this, if we use double magnets to create a stronger magnetic field like this, the coil generates even more current. Now, let's try to generate a continuous current. At the center of this model is a rotary magnet. A coil is wound around the magnet. We rotate the magnet. You can see the needle of the microammeter start to move. When we turn the magnet faster, the needle moves more. As the speed of rotation of the magnet increases, that is, as the coil cuts across more magnetic lines, more current is generated. These experiments show the following principles. The faster the conducting wire cuts the magnetic field, the more current is generated by electromagnetic induction. The more current conducting wire wound around a coil, the greater the induced current. The stronger the magnetic field, the larger the induced current. These 3 points are very important because they are basic to knowing how to control the amount of power the alternator generates. Now, we'll look at the alternator that is actually used in a car. We will explain how the most widely used type of alternator works. That is, one equipped with an IC regulator. The alternator consists of a pulley, frames, a stator, a rotor, an IC regulator, and a rectifier. The last 2 parts will be discussed later. In the alternator, the rotor corresponds to the magnet you saw in the experiments. The rotor consists of a rotor shaft, 2 cores, a rotor coil, 2 slip rings, and so on. When the current flows to the rotor coil through the slip rings, one of the cores becomes the north pole and the other becomes the south pole. That is to say, the rotor becomes an electromagnet. The strength of the magnetic field can be changed by varying the amount of electric current supplied to the rotor coil. The next component is the stator. The stator corresponds to the coil in the first experiment. When the rotor rotates inside it, an electric current is generated in the coil. 3 coils are wound around the stator, and they are connected together at one end, which is called the neutral point. This is a circuit diagram of the stator coils. This is called a Y connection, and the point of connection in a Y connection is the neutral point. Now, using an oscilloscope, let's observe the current generated in the coils of the stator. You can see that an alternating current is being generated. This is actually a 3-phase alternating current. It is very important to notice that the current generated in the stator is an alternating current, not a direct current. That means that it cannot be used in a car as is. This is because all the electric components in an automobile work on a direct current. Direct current is also needed for charging the battery. So how can we obtain a direct current from alternating current? This is done by using a rectifier. The rectifier, which is a device for converting AC to DC, is installed on the rear end frame of the alternator. The circuit diagram shows that it contains several diodes, which allow current to flow in one direction only. Before we continue, let's discuss the principle of rectification based on a simplified circuit diagram. When terminal A of the alternator is positive and terminal B negative, current flows like this. However, when the polarity of the alternator reverses, the current can't flow in the opposite direction because of the diodes. This means that current flows only in one direction through the load. That is, direct current is produced. This is what we mean by rectification. The alternator produces three-phase alternating current, so the direct current after rectification is as shown. This is what a rectifier looks like. One more problem remains, however. The rotation of the engine varies according to the vehicle speed, and the faster the rotation of the engine, the more current is generated. The electrical and electronic components of automobiles, however, can only operate with voltages in certain ranges. So, excessively high voltages can damage the components or overcharge the battery. To avoid this, the voltage that is generated by the alternator must be kept within a certain range. Let's look at the regulator which controls the voltage generated by the alternator. The voltage regulator is installed on the alternator beside the rectifier. Its internal construction is as shown. It consists of a hybrid IC having a built-in monolithic integrated circuit, transistors, and so on. Please note that this type of regulator cannot actually be taken apart. Now, we will explain how the voltage regulator works. First, battery voltage is applied to the rotor coil of the alternator. Then the alternator rotation speed is gradually increased. Let's measure the voltage generated at terminal B, which is the alternator output terminal. As you can see, the voltage increases steadily. If this continues, the electrical components will be damaged and the battery will be overcharged. As we explained when we talked about induced current, there are three ways for varying the generated current: the speed at which the magnetic field is cut, the number of coil windings, and the strength of the magnetic field. If one of these is changed, the generated current changes also. With the alternator, however, the speed at which the coil cuts across the lines of magnetic force depends on the rotational speed of the engine. Furthermore, since the number of windings is of course fixed, the voltage can only be controlled by changing the strength of the magnetic field. We now put a variable resistor between the rotor coil and the battery. When the rotation of the alternator decreases, we can increase the current to the rotor coil by reducing the resistance of the variable resistor. This will strengthen the magnetic field of the rotor. On the other hand, when the rotation of the alternator increases, we can decrease the current to the rotor coil by raising the resistance. This weakens the magnetic field of the rotor. As you can see, this time the generated voltage did not increase. In short, the regulator functions like a variable resistor. The regulator controls the current in the rotor coil according to the engine speed, thereby maintaining the alternator output voltage within a predetermined range. Next, we will explain the operation of the charging system using a circuit diagram. focusing especially on the current generated by the alternator and its control by the regulator. When the ignition switch is turned on, current from the battery flows to the IG terminal. The MIC senses this and turns transistor TR1 on. As a result, the current from the battery goes through the terminal B to the rotor coil, which is consequently magnetized. At this moment, to control the discharging of the battery, the MIC keeps the current to the rotor coil below 0.2 ampere by repeatedly switching transistor TR1 on and off. Current is not produced yet, so there is no voltage at the terminal P. The MIC senses this and turns transistor TR2 off and transistor TR3 on. The charge warning light, therefore, goes on. Next, the engine starts. As the alternator starts to generate, the voltage at terminal P increases. The MIC senses this and switches transistor TR1 from the intermittent on and off state to a continuous on state, causing exciting current to be supplied by the battery to the rotor coil. On the other hand, when the voltage at terminal P rises, the MIC turns transistor TR3 off and transistor TR2 on. As a result, there is no potential difference between the ends of the charge warning light, so the light goes off. When transistor TR1 is on, and the voltage at terminal S reaches a standard value, the MIC turns transistor TR1 off. Consequently, the current to the rotor coil is cut off, and the voltage at terminal S falls below the standard value. In other words, the voltage of the generated current drops. On sensing this, the MIC turns transistor TR1 on again, allowing currents to pass through to the rotor coil. In this way, the generated voltage is kept at a uniform level by the intermittent sending of current to the rotor coil by transistor TR1. In addition to controlling the voltage, the regulator also detects the faults shown here. When one of these faults occurs, it turns on the charge warning light. These two diodes are called neutral point diodes. When the rotation of the alternator exceeds about 2000 RPM, the output at the neutral point becomes higher than the alternator output voltage. These diodes use the excess voltage to raise the output of the alternator by 10 to 15%. To summarize about the charging system, the alternator produces alternating current. The rectifier converts the alternating current into direct current. And the regulator keeps the voltage produced by the alternator steady. Finally, we'll look at troubleshooting of the charging system using the main faults in the system as examples. One of the commonest faults is a flat battery. However, a flat battery is not always caused by a fault in the charging system. There are also other causes. One of the causes is deterioration of the battery. The other is overload. In other words, the vehicle is provided with more electrical components than specified by the manufacturer. Another problem is that the battery cannot be fully charged because the car usually drives only short distances. You should make sure of the following before investigating the charging system. Is the electrolyte level and the specific gravity of each cell of the battery correct? Are the battery terminals, the fusible links, fuses, and connectors connected correctly? You also need to check to see whether additional electric components have been fitted and how the vehicle is driven. After checking each of these items just mentioned and ensuring that they are normal, we are ready to inspect the charging system itself. The first cause of the flat battery caused by a charging system fault is insufficient alternator output. One cause of insufficient alternator output is slippage of the alternator drive belt. If the belt slips, the rotation of the alternator will decrease and the output will be insufficient. First, make sure that the belt tension is correct and there is no excessive wear or cracking of the belt. If necessary, replace or adjust the belt. Another situation is when the generated voltage is lower than normal. The cause is insufficient output due to a fault in the alternator or the regulator. In this case, find the problem by conducting a no-load test of the charging system. If the generated voltage is lower than normal in this test, recheck it after grounding terminal F to apply the battery voltage directly to the rotor coil. If the generated voltage goes above standard value as a result, there could be a fault in the regulator. If the voltage is still too low, on the other hand, a fault in the alternator is likely. In that case, the alternator must be checked. Another typical fault is overcharging of the battery. If the battery is overcharged, a lot of bubbles will be seen in the electrolyte, and the electrolyte will decrease considerably, and the light bulbs and fuses will not last long. This is probably caused by overvoltage from the alternator. This in turn is due to a malfunctioning regulator, which allows too much current to flow to the rotor coil. You can also check for this by carrying out a no-load test. In this test, if the generated voltage is higher than the standard, recheck after replacing the regulator. If all voltage generated by the alternator is within standard, you can make your final determination of the charging system condition by doing a with-load test. In the with-load test, if the amperage generated by the alternator is at standard or below, you can assume that the alternator is at fault and inspect or repair it as necessary. You can refer to the repair manual for the relevant engine details, how to carry out a test with and without load, and how to determine whether the charging system is otherwise normal or not. We started this video presentation with the principle of the generation of electricity, then studied the charging system. Looking at the construction of the main components, we then studied the operation of the system and finished with troubleshooting of the system. We hope that what you've studied in this video will be of help to you in your daily work.